All right, here we have the notes for section 2.1, linear and quadratic functions and modeling. So first we've got a definition of a polynomial. So n is a non-negative integer, and a0, a1, 2, 3 be real numbers with an not equal 0. That gives you the function with that general form. That's referred to as a polynomial of degree n. The leading coefficient is an. Zero function f of x equals 0 is a polynomial function. It has no degree and no leading coefficient because it's just 0. So if you look at example 1, it asks which of the following are polynomial functions. For those that are polynomial functions, state the degree and the leading coefficient. For those that are not, explain why. So this first one would be yes. For those that are, state the degree. So the degree for this problem, so the degree is the highest power, so the degree is 3. The leading coefficient is just the coefficient on the term with the highest power. So if the highest power is 3, the leading coefficient is its coefficient, or 4. For g of x, this one will be no. You have a negative exponent. So at the top it says n is a non-negative integer. For h of x, also no, because of the square root. And for k of x would be yes. The degree, all right, is the highest power, so that is 4. And then the leading coefficient is the coefficient on that term, or 2. All right, on the top of the next page, we have some just definitions of different kinds of functions. So you have the 0 function, which is just equal to 0. It doesn't have a degree because it doesn't have any x terms. Constant function is equal to some number a. It has degree 0. Linear function, ax plus b. You're probably more familiar with this as mx plus b, has a degree of 1. And then a quadratic, ax squared plus bx plus c, where a is 2. Now these a not equal 0 things are important because if, for example, in the quadratic, if a is equal to 0, that term disappears and you're just left with bx plus c, which is the same thing as a linear function. In a linear function, if a is 0, this becomes b, which is the same thing as a, or a constant function. And in this case, if a is 0, then you just have a 0 function. So the next thing we've got here, linear functions and the graphs. So a linear function is a polynomial of degree 1, and so has the form f of x equals ax plus b, where a and b are constants and a is not 0. So normally these draw lines, that's why they're called a linear function. So for example 2, it says write a linear equation for the linear function f such that f of negative 1 is equal to 2 and f of 3 is equal to negative 2. So this notation is based off of this, f of x is equal to y. So these things are actually pairs of coordinates. This coordinate is negative 1, 2, and this coordinate is 3, negative 2. So to write the equation of the line, I need its slope first. So m equals y2 minus y1 over x2 minus x1. So that's going to be negative 2 minus 2, y2 minus y1 over x2 minus x1, x2 and x1. So that's negative 4 over positive 4, so that slope is negative 1. So to write the equation of a line, I use the point slope equation, which looks like this, and fill in my values. So y equals m x. Now I can choose any x value I want. I'm just going to use the first one. So plus 1 because it's minus, and that's already negative, and then plus 2. So that's the equation of a line. Now notice it doesn't say in slope-intercept form, so you are free to stop there. If you wanted to go slope-intercept, you'd have to distribute and then combine your like terms. So that'd be negative x minus 1 plus 2, or negative x plus 1. Okay, so average rate of change. I'm not going to spend a whole lot of time going over this. It has this form, but average rate of change is the slope of the line. So that m equation we used before, which shows up right here, is just the rate of change. So it's the slope represented by m, rise over run, change in y over change in x, delta y, delta x, or the version we used, y2 minus y1 over x2 minus x1. Excuse me. So this is just a summary for a linear function. Now there's your mx plus b form, where m is the slope. So here we've got correlation and linear modeling. So if you plot your points as a scatter plot, you can use your calculator to find a line that passes, or a line that best fits it, so a line of best fit or a regression line. So at the top of the next page, we have the different types of correlation. So in this case, this is referred to as strong and positive. Strong refers to how wide or open the oval is, essentially, or how close the points lie to a line. Positive refers to how the y value changes as the x value. So positive means the y's are increasing, so this is positive and that is positive. Decreasing means the y's are going down, so here and here. These two are strong because the ovals are narrow. These two are weak because they're wide, and this is barely even ovalish at all, so that has essentially no correlation or very little correlation. Sometimes you'll see your calculator or someplace will display the value of r. R refers to how good the correlation is. So r is always between -1 and +1. When r is more than 0, it's a positive correlation, meaning the y's increase. When r is less than 0, it's a negative correlation, meaning that the values are decreasing. The closer r is to 1 or -1, the stronger the correlation is. So that's why I have the opposite value here, because -1 r value means it's very strongly negative, so that'd be this one, and r +1 would be this one. When r is 0, you have weak or little correlation, so that's this one. Okay, example 3 here is going to have us do the regression line. So it says use the data to write a linear regression model for demand, so I'm going to let my calculator handle this. So 2.4, so this is where you go to your stats menu. 2.6, 2.8, 3.0, 3.2, 3.4, 3.6, and then 3.8, 3.20, 3.3710, 2.8280, 2.6550, 2.5530, 2.2170, and 1.8260. Calculate the regression line. So, calculator gives me this equation, y equals, sure. Check my numbers real fast, 28280. $240, oops, there's the problem. That's 2.8. There we go, okay. So it gives me this. Plus, so that's the line that my calculator gives me. So it describes the strength and the direction. So my calculator also handily gives me my R value of -0.98. So this is strong because the absolute value is close to 1, and it is negative. It says then use the model to predict the weekly cereal sales if the prices drop to $2 or raise to $4. So that's just giving you a value to plug in for X. So at $2, your equation becomes y equals -15,358.93 times 2. And that's -5,358.93 times 2 plus 73,622.5. So y would be 42905 rounded. So at $4 a box, y becomes this equation, but I'm going to plug 4 in. And then numbers go in my calculator. And I get 12187 rounded, which makes sense. As the price increases over here, the box is sold, decreases, so the cheapest box should sell the most expensive box should sell the least. All right, quadratic functions and their graphs. So we've talked about quadratics before. They have the form ax squared plus bx plus c. So this is just a reminder of how transformations work. So the +3 here moves the graph up 3 units. The 1/2 is a vertical stretch, and then the negative sign flips the graph. So down here, this one's going to move it down 1 unit. This is going to move it left 2, because inside parentheses is the opposite behavior, and this is a vertical stretch by 3. So you also have quadratics. If you graph them, they have something referred to as the axis of symmetry, or the axis. It's the point that the parabola is mirrored about. So if I have just a parabola floating up here, the axis of symmetry passes straight through there. That point where the axis hits the parabola is referred to as the vertex. So the dashed line in this case is the axis. Where it crosses through the parabola is the vertex. So here is the standard form, the one I'm familiar with. You can convert it to vertex form by doing what's called completing the square. So it says, use completing the square to describe the graph of this. So here's how completing the square works. So the first thing we do is we're going to draw parentheses around our x terms, and then factor out whatever the coefficient on the x squared term is. It's going to look like that. Then you take whatever that number is and divide by 2 and square. So that's plus 4. 4 divided by 4, or 2 is 2, 2 squared is 4. Now I've magically created a number here, which means I need to keep track of it outside the parentheses with its opposite value. Now it looks like I added a 4, but I actually added 3 times 4, which is 12, which means outside I have to subtract 12. Now I can factor this set of parentheses into 2. This is going to be minus 1 at the end. So x and x. So I'm looking for two numbers that multiply to 4 and add to 4. They are both 2's. Now when you complete the square, these should always come out to be the same, because the goal is to get something squared. That's why it's complete the square. Since there's 2 copies, I can just write it with a squared. Now the shortcut to get these two numbers, it's always half of that number. Half of positive 4 is positive 2. So both positive 2's. So this graph is actually the one we just did. Vertical stretch of 3, moved left 2 units and down 1 unit. So this is the vertex form, so that's what our answer looked like, A, H, and K. There are shortcuts to find H, they're right there, and K right there, without having to go through the completing the square steps. So 6 here says use it vertex form to find the vertex and the axis graph of this equation. Rewrite the equation in vertex form. So before I start, I need to put my terms in order. So the negative 3 is my A, the 6 is my B, the negative 5 is my C. So to find H, that's negative B over 2A. So that's negative 6 over 2 times negative 3. So that's negative 6 over negative 6, which is 1. For K, that's C minus AH squared. So for that problem, C is negative 5 minus A, which is negative 3, times H, which is 1, squared. Now powers come first, so this is going to become negative 5 minus negative 3 times 1. 1 squared is 1. So this is negative 5 plus 3, which is negative 2. So filling the values in, y equals A, which is negative 3, x minus h squared plus k. Now it's a minus there because k is a negative number. So the vertex is always at h comma k, so 1 comma negative 2, h and k. The axis is always x equals whatever the x value is. So in this case, it's 1. Okay, so this just gives you the summary for a quadratic. So use the model of this to develop a model for the weekly revenue donated by cereals, determine the maximum revenue and how to achieve it. So this tells me how many boxes I sold. So if I want my revenue, that's the number of boxes I sell times how much each box costs. So this becomes negative 15358.93x squared plus 73622.5x. Now, what it's asking for here, so this is a parabola, it's going to open down because it's negative, it's asking for the vertex. So I need to find my value for h and my value for k. So h is negative b over 2a, so that's negative 73622.5 over 2 times negative 15358.93. So negative 73622.5 divided by 2 times negative 15358.93. So this is, since x is money, That's, whoops, $2 and, yeah, rounded, it'd be $2.40. And then K is going to be what I get when I plug it into this equation. Oops. Minus H squared. So C for this problem is 0, because there is no number. A is the negative 15,358.93, and H is 2.40 squared. So 2.4 squared times 15358.93. So that is K equals 88467 boxes. So selling that boxes will give me the, that's the revenue. Oh, sorry, this is now, since this is Y, my equation is R, that's the amount of money I'll make. So if I sell my box at $2.40, I'll be doing the best. So this one down here just refers to an object in free fall. So this is a quadratic, except that it uses t's instead of x's. And then you have this equation here. So example 8 is asking us to do, it says use the data in the table below to write models for the height and vertical velocity of the rubber ball, then use these models to predict. So I'm going to go back to my stats menu and enter these, but I'm going to model it with a quadratic. So 0.1080, 0.2150, 0.3225, 0.43, 0.5375, 0.645, 0.7525, 0.8600, height 1.03754, 1.40205, 1.63806, 1.77412, 1.80392, 1.71522, 1.50942, 1.21410, and 0.83173. So I'm going to go back to our same place to do regression, except now I'm going to use x squared. So my equation is S of t equals negative 4.67 t squared. My v value plus 3.75 t, and then plus 1.04, which makes sense because that's 1.04 there. So the velocity equation, if you look back at your formula, it uses v0, which is the coefficient on this value. So it's 3.75. Oops, sorry. Since we're doing meters, it's going to be negative 9.8 t, because it's, if you look back at the formula, it's negative g. It tells you what the value for g is. That's really bad. Can't quite get it on the screen there. So you can flip back. And then it's plus v0, which is the b value. So plus 3.75. So those are our two bottles. So it then says, use these models to predict the maximum height of the ball and its vertical velocity when it hits the face. So the maximum height occurs at the vertex of that equation. So I'm going to figure out the vertex here. I'm going to skip the math, but you do it by finding the h and k method. Plus so the maximum height of this object is now the k value, which comes out to be 1.79, and then so that's maximum height and vertical velocity when it hits the face. So to figure out when it hits the face, we need to know where this equation is 0. So I'm going to just use the graph to do that. I'm going to find the roots. So it hits the ground when t is equal to 1.02 seconds. So then I plug that in there. Negative 9.8 times 1.02 plus 3.75. 9.8 times 1.02 plus 3.75. So negative 6.25 meters per second. Now, just a note, if you look at this value here, it's 1.79 meters. If you look in your table, you do have a value more than that. This happens because we rounded these numbers. So that's where we're getting the difference into values for. So you could have actually looked over here and used that to approximate it, but you can't guarantee that it didn't go more than 0.80 in between these two values. You don't know that it's still, whether it's still climbing between here and here, or whether it has started to fall already. So that's why you have to check the math anyway. Even though your number did not come out to be exactly right, it's a better estimate than just guessing. And this down here makes sense. It's going to hit the ground at about 1 second, because if you look at the heights, they are decreasing. So it's 0.83 here. At 0.86, so as the time is going up, the height's going down, so it's going to be more than 0.86. So our 1.02 would be acceptable. And that is the end of this section.